and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In the previous module, we looked at attenuation, which is one of the characteristic of an optical fiber and in general any waveguide, which limits the distance over which one can transmit information. For example, if we actually have a fiber of some length, let us say, we know what is the attenuation of this particular fiber, which we will call as alpha dB per kilometer. Then when I send in optical pulses which carry information, then we know that after propagating through this fiber of length L, the power would be reduced. So, if you had launched a power of P in here, the output power P out will be something like P in minus alpha times L. Now, the reason why we have written minus alpha L, and it is very important to point this out, is that all the powers are measured in dBm units, and dBm units essentially means that if P is the power over 1 milliwatt, what is the ratio of this power over 1 milliwatt, and then you take the log with respect to base 10 of this one, and the result what you get will be the power expressed in decibels meter or decibels milli. So, this is called as dBm units, and all powers in optical fibers are typically measured, or optical communication systems are typically measured in dBm scale. For example, if the power happens to be 1 milliwatt, then in terms of dBm scale, the same power will be actually expressed as 0 dBm. So, please remember this, and since alpha is expressed as dB per kilometer and we have propagated these pulses over a distance of L kilometer, the total loss in the propagation as the pulse propagates from one end of the fiber to the other end is simply given by the product of alpha, which is attenuation or loss coefficient expressed in dB per kilometer, and L being the length which is expressed in kilometer. So, the quantity alpha L will be units of dB, whereas P in will be units of dBm, and one can take into account the gain of a system by adding the gain in decibels to the power which is expressed in dBm scale. So, instead of having this alpha L product being the loss, if it was amplifier which over a length L would have amplified the signal by an amount, say gain of say G dB per kilometer, then the total gain would have been G times L, and that gain will be in terms of dB. That quantity could be added off to the power when the power is expressed in dBm. In fact, this is the advantage of having to use the dBm units or the decibel units. For example, if we have system in which I have an optical fiber of length L with an attenuation of say 0.2 dB per kilometer, and let us say we go over 10 kilometers, just to keep the math simple I am doing this, and then we follow it up by an optical amplifier. We will have to say more about this optical amplifier in the other modules. Let us say this has a gain of about 10 dB. What would be the output power here, provided the power launched into the fiber is say 1 milliwatt. To answer such questions, if you were to actually use the linear scale, would be little uncomfortable, because you have to convert this loss 0.2 dB per kilometer and the overall loss, you have to convert that into the linear scale and then multiply that particular power 1 milliwatt, which is the launch power, by this factor, and then also multiplied by the gain after converting the gain which is given in 10 dB to the linear scale. But using decibel scale throughout and making the first substitution or first conversion from milliwatt unit to dBm, which gives us 0 dBm here, the rest of the output can be very easily found out, because 0 dBm optical pulse is propagating or launched into the fiber. The total loss it suffers will be 0.2 into 10, which is 2 dB. Note that kilometer has cancelled out. So, you started off with 0 dBm, the power at the output of the fiber will be at minus 2 dBm, not dB but dBm, and then you have a gain here, right. So, please excuse the way I have not I have written it here, but because of the gain which was 10 dB, the output power will be 10 plus minus 2, which in actually becomes plus 8 dBm. So, this is essentially how easy it is for us to consider various stages of loss, gain and their combinations. Okay. So, this is the reason why we go to the dBm scale. But let me come back to the problem that we were looking at. We launch an optical pulse with respect to time, let us say, and this is carrying certain information, maybe this is carrying a digital bit information of 1, and then when this passes through the fiber, suffers a loss, then this is what the optical pulse that you are going to get. This optical pulse will be at a lower power level than the input power level, and if you now follow it up with a detector, photo detector, which we will again discuss later on during the course, but for now a photo detector is a device which converts light into electrical current. So, since you have applied an optical pulse, this optical pulse or the light pulse will be converted into an electrical pulse with certain conversion factor. Okay. Now, if the length L were to be made very large, right, then the total loss in the fiber would also, or total loss contributed by the fiber would be so high that the optical pulse that is incident on the photodetector might be too small, okay, for us to actually get any reasonable output. Okay. So, if instead of propagating L over let us say 10 kilometers, when the loss is 0.2 dB per kilometer, if I propagate this one over let us say 1000 kilometers, then the overall loss that I will have will be 1000 times 0.2, which is about 100 dB. So, when you launch an optical power let us say at 1 milliwatt or equivalently 0 dBm peak power, then the peak power that you get at the output of the fiber, okay, which is about 1000 kilometers long with 0 dBm input, would be actually minus 100 dBm. When you go back and calculate what would be the corresponding value in milliwatt, which I will leave it as an exercise to you, this number would be something like much less than picowatt. Okay. This picowatt optical power is unfortunately not, the photodetector unfortunately cannot detect optical pulses of this low intensity or low power. Okay. So, attenuation causes us to actually pick a maximum value of L such that the detector is still able to function, or we pick a value of L and then we start putting the optical amplifiers. Okay. So, that we can boost the signal power as and when the signal power becomes lower. So, this distance before the actual, the distance over of the maximum fiber before we need to place an optical amplifier for the system operation conditions is called as a span. Okay. So, what this attenuation does to our optical pulses propagating in the fiber is to actually reduce the span length. Okay. So, that was attenuation. So, just to summarize the first few minutes that we have talked about, attenuation limits the maximum span length. Okay. So, in fiber optic communications, long haul communications, the span length is standardized at around 80 kilometer, sometimes relaxed up to 100 kilometer, which means to say that you have your launch optical pulses or optical signals, then they propagate through the fiber of length 80 to 100 kilometer before we place an optical amplifier of a certain gain. The gain is usually chosen such that the gain completely compensates for the loss here. Okay. So, this is the number 80 to 100 kilometer has been standardized because you want certain system performance, and this number seems to be very reasonable, okay, given the current attenuation limits of the optical fiber. And I must tell you that the optical fiber attenuation at 1550 nanometer is anywhere between 0.15 to 0.2 dB per kilometer. In the field, this number slightly increases to 0.2 to 0.25 dB per kilometer. Okay. When I say in the field, I actually mean that when you lay down the optical fiber in the form of a cable, there is a slight increase in the loss, whereas 0.15 to 0.2 dB per kilometer is an optical fiber loss itself, which is approximately the value that you obtain from theoretical contributions or theoretical calculations for loss. Okay. So, attenuation limits the maximum span length. So, then there is another characteristic which I have highlighted and which is essentially what we are going to discuss in this and the next module, which is called as dispersion. What is dispersion? If you have taken some communication courses, then you would know what dispersion is and what leads or what essentially the system impairment that is caused by dispersion. There are various definitions of it. In physics, dispersion is normally a term that is used to denote the refractive index dependence on the frequency or the wavelength, okay, wavelength lambda or frequency. So, it is the refractive index dependence, which means that the refractive index is actually not constant as we normally think. So, we say that refractive index of glass is about 1.5, fused silica is about 1.5, but that is not true. That is true only over a certain wavelength or frequency range. Okay. So, even water, for example, will have different refractive indexes at different wavelengths and different frequencies. Okay. So, in physics, when we talk of dispersion, we normally mean that it is the refractive index which is dependent on lambda and f, and this refractive index itself arises because of the structure or the material properties. So, when the material itself or the material refractive index itself is dependent on lambda and frequency, we simply term this as material dispersion. Okay. So, we call this as material dispersion. So, if I were to take a big infinite slab of glass here, then the only type of dispersion that my pulses or optical signals would experience would be this material dispersion. Okay. So, if I take an infinite slab, because I can then put plane waves into it, then the only dispersion that we will see will be the material dispersion. Okay. And what is the result of this material dispersion? You might have launched an optical pulse with respect to time, let us say, with some pulse width of t0. This pulse width t0 is normally measured with respect to the half power points. That is, if you were to plot the power profile. So, if p of t corresponds to the power of the pulse that is launched or the time dependent power that is launched, then from the peak power, which we will not label as p0, you find out 2 points where the power has dropped to p0 by 2, okay, and then find out the time intervals between the two, and the difference in the time interval or the length of the time interval where the power actually is above p0 by 2 is called as the pulse width. It is normally called as the full width at half maximum pulse width. Okay. So, this is very important. This is called as a full width at half maximum pulse width. Okay. It is not the only definition of pulse width. There are various other definitions, but this is the one that is commonly used in practice to talk about the pulse width of optical pulses and what changes does this pulse undergo as it propagates through various optical elements. Okay. As I told you, material dispersion means that in the refractive index, which itself is a property of the material that we are considering, depends on the value of refractive index depends on wavelength or the frequency. Okay. And since when you launch a pulse in time, the corresponding frequency domain picture of this one would again be some sort of a pulse. Okay. So, let me use a red color to indicate that I am considering pulses in the frequency domain. And how do I go from time domain to frequency domain? I have to take the Fourier transform. We will have to say more about that shortly. So, when I am given the time domain pulse, I take the Fourier transform, and once I have taken the Fourier transform, I have gone from the time domain to the frequency domain. And in frequency domain, what we really are saying is that there are all these different frequency components. Okay. Of course, there are an infinite number of frequency components because this is a continuous time signal and the corresponding Fourier transform is also continuous time. Okay. But it is okay to think of this continuous frequency spectrum or the continuous frequency Fourier transform of the optical pulse as composed of many different frequency components, discrete frequency components, and to then look at what happens to the individual frequency component as it propagates. So, let me take this individual frequency component and propagate this one and propagate this one and propagate. Okay. So, because the refractive index n is different for all these values, the corresponding propagation constant, which let us say we either label it as k of omega or beta of omega. Okay. In free space we normally use k of omega. In the waveguide case we use beta of omega. Since we are discussing so far with an infinite slab which is kind of free space, we will use k of omega, and this k of omega will be given by k0, which is the wave vector in free space, given by 2 pi by lambda times n of omega. Okay. So, this is the functional dependence where omega is of course 2 pi f, this omega is actually the frequency. So, what you have seen here is that this k0, which is 2 pi by lambda naught, and lambda naught is usually with respect to some carrier frequency that you would be measuring. In this particular case, it would be the lambda 0 at that frequency omega that you are considering. So, when you actually look at this k of omega, what we are essentially saying is that because n is changing, right, with respect to frequency, right. So, the corresponding propagation constant k of omega is also changing. Okay. So, with the effect which we will show shortly, that when you look at the output back in the time domain after propagation through a length, let us say some L. Okay. So, when you look at the output would actually have spread out. So, in terms of time domain, when you are going back from frequency to time domain after propagation, you would see that this has actually dispersed. Usually it would be spread out. There are certain cases which are anomalous in some sense, wherein instead of spreading out, the pulse actually contracts. Okay. So, these are what we normally term as anomalous regime, and the usual or conventionally spreading out of a pulse regime is what we call as a normal dispersion regime. So, these two are called as normal dispersion and anomalous dispersion. Anomalous means initially or at least over that particular length, the pulse width actually reduces. Okay. So, in fact, this is used to obtain ultra short pulses. So, to obtain ultra short pulses, you actually start with a reasonably short pulse, but then when you repeatedly pass it through a material whose dispersion is negative, or you pass it through a system which can give you a total contribution of negative dispersion, then what you see is that the pulse width becomes smaller and smaller, until there is of course a certain limit of operation as to how much you can compress this pulse. So, this application is called as pulse compression, and it is very widely used in optical signal processing or optical pulse processing. But coming back to this dispersion, which I have shown here is the normal dispersion, and this normal dispersion has arisen because of the refractive index dependence on wavelength and frequency. Okay. So, this is the material dispersion. Now, in optical fibers and in waveguides, you will see that in addition to material dispersion, there will also be another dispersion because of the geometry itself. Please recall that in the optical fiber, because of the geometry that we have drawn, plane waves cannot exist. Okay. So, there are no plane waves simply because the cross sections that we have taken cannot support a plane wave. Okay. In fact, what we have seen is that the optical pulse would actually exhibit a transverse field profile, which would be function of both r and phi, or in the so called linearly polarized modes, this can be considered to be a function of x and y, but nevertheless this is a function of x and y. So, the transverse mode profile, which is essentially how the light distributes itself in terms of the transverse dependence, okay, or the transverse coordinates, is called as the mode of the optical fiber, or in general the waveguide, and we have seen that there is this mode. And we have also seen, or if you have not seen it already, you will see it soon, that the propagation constant beta actually depends on what mode is the light propagating and what is the frequency at which this is propagating. Where have you seen this one? Well, you have seen this when you have plotted these so called B versus V curves, and if you have not seen this earlier, you can see it now, where we define this B as beta square by k0 square minus n2 square divided by n1 square minus n2 square. The entire root of it is by definition what we call as the normalized propagation constant B. If you are uncomfortable thinking of B, you can simply think of this as beta. It is essentially the same thing, okay, because one gives you the other, and B number of course we have defined as 2 pi by lambda naught a square root of n1 square minus n2 square. Okay. If n1 and n2 are constants with respect to frequency, which of course you know that they cannot be, right, because refractive index of the fused silica N1, although we have taken it to be constant, this constant is only for a given wavelength or given frequency of operation. If I change one or the other, then I know that N itself will change because of the material dispersion. But for the moment, if you ignore that complication, then what you will see is that this B with respect to frequency, because 1 by lambda is kind of frequency or proportional to frequency, you see for different modes, right, you see these type of curves where B max is about 1 and it is reached asymptotically, and then you have seen these kind of graphs that you would see. So, this corresponds to LP01 mode. This group essentially as such corresponds to LP11 mode or LP02 mode. I forget that exact this one, because normally I deal with only single mode fibers. Okay. But nevertheless, the point here is that you are now looking at propagation constant, which is different at different modes, as well as around that mode how exactly this is varying. So, this variation is both in terms of mode as well as in terms of frequency at a given mode itself. So, when you fix mode, since you are varying the frequency, so around this the propagation constant would vary, or if you were to fix frequency, but you actually have multiple modes, whenever there is multiple mode, for example in this case, right, then at this frequency then you have one dependence corresponding to LP0, LP11 mode for example, and then there is another dependence at the other mode LP01. Okay. So, you have these type of dispersion, which is the result of trying to instead of letting the light go as a plane wave, but trying to kind of confine that plane wave into certain guiding structures. This type of waveguide is called, this type of dispersion is called as waveguide dispersion. Okay. It is the geometrical nature of the waveguide that largely determines this waveguide dispersion. Okay. So, the slope here of the blue curve, which is the propagation constant versus frequency, normalized frequency, will depend on whether we are considering a slab waveguide or we are considering a optical fiber. Okay. And the exact shape as well as the modes all depend on the type of waveguide that we consider. So, these are the two types of waveguides. We will now look at something without first looking at what is this material dispersion. Since material dispersion is largely material properties, I do not deal with material dispersion in anymore, but I will have something to say about waveguide dispersion. But both these dispersions we will have to relate it to transmission characteristics. Okay. So, what I do is to actually show you the general idea behind dispersion and how it affects the optical signals propagating, and then come back and revisit this waveguide dispersion. Okay. So, let us start by looking at a general channel which could be an optical fiber or it could be any other thing. I am assuming that the channel has a certain length L, and for now, for the moment, we ignore attenuation. So, we take alpha to be equal to 0 dB per kilometer. So, this discussion that we are about to have can be applied to waveguides which work in the optical frequency, that is to say optical waveguides, or this can also be used to understand rectangular, circular or the other guides which are metallic waveguides. You can also include slab waveguides, you can include copper wires in this, for example. So, the general formalism that we are going to discuss now is valid for all the different type of channels. I am not specifying what the channel thing is, except to say that the propagation constant beta, okay, is a function of frequency, which I will denote it as beta of omega. Okay. Our goal is to understand what happens to a pulse which is propagating. So, this is an optical pulse. This pulse would usually be modulated onto the optical carrier as well, but for now I am not writing it. Okay. So, since this is the optical pulse that I am considering, although as I told you the formalism can be used for everything, any other waveguide. So, since it is optical pulse in this context, so this I will write it as E and write this as 0 comma t. Okay. This is interesting. Why have I written this as 0 and t? 0 refers to the input of the channel, which we will take at z equal to 0, and at the output which we will take at z equal to L. Okay. So, at the input I have an optical pulse, this pulse I have shown only in this format, it could be any other optical pulse, okay. And what will happen to this optical pulse at the output is what we want to understand. If I were to try and directly analyze how this electric field would actually propagate through the channel, I would be failing. Okay, by the way, you also note that I have not put any vector sign on electric field, because in my mind I have kind of assumed a scalar approximation for the pulse that is propagating, which means that for the LP modes we know that light can be polarized along y or it can be polarized along x directions. So, you pick only one of the directions and then you look at what happens to this one. Okay. There are various ways of handling both degrees of freedom, and that leads to something called as polarization mode dispersion in optical fibers. That is the subject of another module another day. So, right now I am looking at electric field, and also I am now going to assume that the mode shape, that is f of x comma y or f of r comma phi, essentially remains constant, and it is the same for different modes. Okay. This is a highly simplifying assumption, okay, because I am only interested in looking at what is the effect of propagation constant beta depending on omega. I will assume that the mode shapes more or less remain the same, as they propagate. Of course, when you have multimode propagation, this assumption is not true, but what we will assume is that once you have a certain set of modes, for example, here you have certain mode LP01, I mean LP11 for example, and then you have an LP01, you will also have LP02 mode. The mode shape here would be by and large independent. This is the LP11 mode. So, you will have an LP02 mode. So, this shape would not depend on frequency. That is a reasonable assumption to make. So, the shape remains the same as the pulse propagates. Okay. So, now how do I go about trying to find out what is the interest to me? My interest is to find out what would be the output electric field at the output of the channel. Okay. Of course, as I told you, this can be applied to any general characteristic. So, instead of talking about E of 0t, you simply talk of G of 0t, where G of 0t would be the input pulse at the input of the channel, and G of LT would be the output pulse or the pulse at the output of the channel. Unfortunately, I cannot work in the time domain if I want to understand how to obtain this electric field at the output. So, if I want to understand the pulse propagation, unfortunately I cannot do it in this time domain, I will have to do it in the frequency domain. And the basic idea that we are going to use is very simple. We are going to convert this into the frequency domain, okay, by going through the Fourier transform, which will land us with E of 0 omega. Okay. Let me put another symbol to denote what I am writing here is in the frequency domain. So, what I will have is the spectrum of the pulse that is now trying to propagate through the channel, and using this spectrum is what we will build to the output and then go back from frequency domain to the time domain using the inverse Fourier transform, something that we are going to do in the next module. Thank you very much.